Hello, everyone. Welcome to a new lecture of our course on heterogeneous systems. Today, we continue talking about GPU programming, but we start a new part of the course. After having introduced the GPU architecture and the basics of GPU programming and optimization, now we start talking about parallel patterns. And in particular, we are going to focus today on the reduction. A parallel pattern is essentially a way of dividing the data parallel computation over the available workers, in this case, the GPU threads. In the end, parallel patterns are applicable to any other data parallel architectures, but we will focus mostly on SIMD processors and GPUs. Let's very quickly recap on what we have covered in the previous lectures. Remember that in the last lecture, we were talking about main GPU performance considerations. Remember as well that the typical program structure in heterogeneous computing systems with CPUs and GPUs, what we would normally do is executing the sequential or modestly parallel sections of the code on the CPU and the massively parallel sections of the code on the GPU. We would normally have a CPU thread, running some serial code or modestly parallel code, as I said, then at some point launching a GPU kernel that will run on the GPU with a certain grid composed by a certain number of blocks and a certain number of threads in each block. And after the kernel termination, control will go back to the CPU that can execute more serial code and then eventually launch a new GPU kernel. Remember as well the memory hierarchy in CUDA programs where different threads sharing in the same block can access their own registers, but they can also share data using this shared memory. There is an on-chip scratchpad in each GPU core. And thread blocks and threads belonging to different thread blocks can access common data from global memory or constant memory that are off-chip. Remember as well regarding GPU optimization, GPU program optimization, remember as well that it's important to try to take advantage of the latency hiding mechanisms that fine-grained multi-threading architectures provide, and GPUs are fine-grained multi-threaded architectures. These fine-grained multi-threading mechanism allows us to hide long latency operations by executing other operations. For example, in a GPU, we can hide accesses to the off-chip memory that is typically our long latency operations. We can hide these long latency operations by executing other instructions in the pipeline. And in order to do so, it's important to make sure that the available number of threads and warps in the GPU that can execute instructions and are ready to execute instructions is high enough. And that's what we call the occupancy. Remember as well that in order to have efficient access to the global memory, to the off-chip memory, it's important to try to coalesce the memory accesses. That essentially means that threads that are executed together access memory locations that are nearby. And if these memory locations are nearby, they will be in the same DRAM bars and they will be served at the same time. However, if the memory locations that different threads in the warp access are not in the same warp, we would probably would need more than one memory transaction, and that will, in the end, affect the available bandwidth and the bandwidth that we can achieve. And that's what we call memory uncoalescing or memory divergence. Here you see two examples of a coalesced and a non-coalesced memory access. In the coalesced memory access, we have threads that run together, executing nearby memory locations, and over successive iterations, they go and continue accessing nearby memory locations. In a non-coalesced memory access, there's threads, neighboring threads, as these thread 1 and thread 2 here, are accessing locations that are distant from each other in memory. One way of improving the memory access, one way of improving coalescing is to use shared memory. And in order to do so, well, shared memory can be very useful to take advantage of data reuse. It's something that we already discussed in the previous lecture, but shared memory is also useful to improve coalescing. If we have a matrix that we are going to access with an uncoalesced memory access from the global memory, one thing we could do is dividing this matrix into tiles, bring the tiles to the shared memory or the scratchpad, and access them from there. This way, we would be avoiding the uncoalesced or we can avoid the uncoalesced memory accesses to global memory and have more efficient access for neighboring threads. Remember as well, another important performance consideration is to maximize the SIMD utilization or the warp utilization, or the other way around, avoid the warp divergence. And that's something extremely important for the efficiency in not only GPUs, but SIMD processors in general. Remember that in GPUs with the single program, multiple data programming model, it's possible to write different control flows for different threads that might be even executing together in the same warp. However, if that happens, and even though the hardware can support it by the use of predication or mass execution, if that happens, we have branch divergence or warp divergence. And what that means is that threads executing together in the same warp will have to split, and some of the threads that will go to one path will run at the same time, while the others will have to wait until we can execute the other path. And at some point, they will reconverge, as you see. So this is definitely supported by the hardware, but as you see, we are reducing the utilization here in this part. So the performance of the of our code as well. We are going to discuss today ways of improving this warp utilization with one important example, that is the parallel pattern reduction. Here you see another example of how to exploit the SIMD utilization better. In this particular simplified code that you see here, we have some intra-warp divergence, and this happens because we have even threads doing part of the computation or some computation, while odd threads or odd number threads are doing different computation. In the end, what happens here is that after having executed together all the threads in a warp, then only half of the threads execute the if, and the other half of the threads execute the else. What that means what this finally means is that we will need essentially twice the number of cycles to execute the if and the else. In a divergence-free execution, what we do is rearranging the way that we assign threads to data in a way that we avoid the intra-warp divergence. Observe that in this code, we have exactly the same computation as in the previous code, but in this case, assuming that in total we have 64 threads or 2 warps, what we are doing is that the lower warp, warp 0, or those threads with an ID lower than 32 are executing the do this part, while the other threads, those with a thread ID higher than 32 or greater or equal to 32, are executing the do that part. And as you see, now we have divergence-free execution here in the else, and divergence-free execution here in the if and also in the else. And that's what we should try to do in all our programs in order to increase the SIMD utilization. And one of the operations that can benefit from this improved SIMD utilization is the reduction operation. Let's start defining what's a reduction and talking about where it's used. A reduction is an operation that reduces a set of values to a single value by using a particular operator, which might be sum, product, minimum, maximum, or others. This operator needs to have certain properties. It needs to be associative, it needs to be commutative, and it needs to have an identity value. In the case of the sum, for example, we know that sum is associative because we can change change the order that we perform the additions when we have multiple elements that we have to sum. It's commutative because we can swap the summands. There is an identity value that is 0, because if we add 0 to anything, the result will be the same original value. And reduction is a key primitive in parallel computing. For example, it's used in the map-reduce programming model. Let's start talking about how to perform a sequential reduction. A sequential implementation of reduction only needs a for loop to go through the whole input array. We have n elements and we will need n iterations. So a sequential reduction, we can say that it has a complexity On, right? This is our input array with n elements from A0 to n-1. And this is a very simple code that we can use to perform the sequential implementation of reduction. Observe that we initialize an accumulator with the identity value, because in this case, the reduction is using addition, the identity value is 0. And now with this for loop, we go over all the elements of the input array and we accumulate the values of all elements of the input array A into our accumulator. After the n iterations in this sum variable, we'll have the reduction result. There are many independent operations here, and a parallel implementation can calculate multiple partial sums and then reduce them. Observe that all these additions are independent or could be done in an independent manner of each other. Why is that? Because the sum is associative and it's also commutative. So we can, for example, divide the whole computation here and have, like, let's say, 2 threads, one of them reducing all the values in the lower part of the array, and another thread reducing all the values in the upper part of the array. And that's essentially what we are going to do in the, let's say, most typical pattern for reduction, that is the tree-based reduction. So what we do here is performing the reduction in successive iterations, and in each iteration, we are going to assign 2 elements to a single thread, to a single worker that will perform the addition of these 2, and then we will go to the next iteration. So in the first iteration, we will assign threads to every 2 elements. We perform an addition and obtain some partial result that we keep in some temporary storage. In the next iteration, observe that half of the workers, half of the threads will retire, but the ones that remain continue performing additions, performing the reduction and accumulating the partial results in some temporary storage. In the third iteration, observe that now, after the third iteration, we only have 2 more values to add, and in the last iteration, we will have a final thread performing the final sum. So in total, we need, for an array of n elements, we need log n iterations for this tree-based reduction. So as you see, it's already more efficient than the sequential reduction that we showed in the previous slide. And this tree-based reduction is the way that we are going to implement reduction on a GPU. In this case, what we will do is dividing the input array into the available thread blocks. Let's imagine that we have 2 thread blocks in this example, block 0 and block 1. And also inside each thread block, we assign computation to threads and to warps. So this part of the array could be assigned to warp 0, to warp 1, and the same for the other thread block. So then we start the execution, and in the very first iteration, we will have some threads performing these partial additions here and storing the partial results in some temporary storage. This temporary storage might be, for example, shared memory or also registers. For now, we would assume that we store these partial results in shared memory. Observe as well that we are dividing the array across thread blocks and across warps. So for those threads that belong to the same block, we'll have to do some intra-block synchronization, some sync threads. We need to use sync threads here. And why is that? Because threads belonging to different warps, but in the same thread block, are writing to shared memory the partial results. And that's why we have to synchronize so that the results are stable in the shared memory, or these partial results are stable in the shared memory before other threads of the warp or the same thread block go to the shared memory to read these partial results and perform the next iteration. So here you observe that after 2 iterations in this specific example. We have 2 more values to add in each thread block. So we need to perform 1 more intra-block synchronization, and finally we would obtain a single value per thread block. So this value here corresponds to the partial reduction in block 0. This corresponds to the partial reduction in block 1. But now we have to continue reducing because we may have 2 thread blocks or we may have many more. And in the end, we want to obtain a single value as the result of the reduction operation. So because this is being executed by different thread blocks, we need some way of doing some inter-block synchronization. And there are different potential ways of doing inter-block synchronization. The simplest one is to do kernel termination and then move these partial sums to the CPU and performing the final reduction on the CPU. In some cases, if the size of the original array is huge, and after having performed these partial reductions in the different thread blocks, we still have many elements here, we may want to launch a new kernel, a new reduction kernel on the GPU. And finally, one other way is to use atomic operations in global memory, because at this point here, we have a single value per thread block. We could have one thread per thread block accumulating this value into a global variable, an atomic variable in global memory, and we would only need 1 atomic operation per thread block. That's something that we can do. It may have also its drawbacks, because as you remember from our previous lecture, atomic operations serialize the execution, but because we are only using it at the very end of the reduction, it might still be worth it. We will talk again about this possibility at the end of the lecture. In the end, we will obtain a final result that will be the reduction result. So let's see how to map this tree-based reduction on GPU, now taking into account other considerations related to the performance and optimization of our code. We could start doing a naive mapping of threads to computation, and because in the end, in the parallel reduction, in each iteration, every thread that is active is adding 2 values. One thing we can do is assigning the even number threads to the sums that we have to perform, and observe how here thread 0 is going to perform the addition of element 0 and 1. Thread 2 performs the addition of element 2 and 3, thread 4, the addition of element 4 and 5, and so on. In the next iteration, half of the threads retire, and now we have thread 0 performing the addition of these 2 partial results. Thread 4 performing the addition of these 2 partial results, and so on. And this is in iteration 3, and in the final iteration, we perform the last addition. The problem with this mapping, with this naive mapping, is that it's a program with low SIMD utilization. And let's see why this happens. This essentially happens because half of the threads are retiring in every iteration, and the threads that remain are those threads that are at a distance 2 times the stride. So there are threads in the same warp that are retiring, while other threads in the warp continue executing. So for example, if in the beginning our assignment is something like this, after 1 iteration, or in the first iteration already, half of the threads are idle. And in the next iteration, even more threads of the warp are idle. But observe that we still have threads active in every single warp. What that means is that we are launching instructions for all the available warps, but only some of the threads of these warps are active, while the other threads are inactive, and in the end, we are wasting those SIMD lanes, right? And it's, well, that would be the next iteration. So as you see, there is a lot of warp underutilization here. So what can we do to avoid this warp underutilization, or at least to minimize it? Well, we can try this divergence-free mapping, where we are going to try to keep active threads belonging to the same warp. or we should try to have all active threads belonging to the same warp or to the same certain number of warps. So what we would do, instead of assigning computation to only odd number threads or even number threads, what we do is assigning computation to the threads with the lower thread ID. So for example, here to perform the same computation, we can have threads from 0 to 15, the 16 threads with the lowest ID, we have them active. And the way that we assign the computation is that such that thread 0 performs the addition of element 0 and element 16, thread 1 performs the addition of element 1 and element 17, and so on and so forth. Observe that this is not going to change the final result of our reduction, essentially because the operator that we are using is addition, and addition is associative and is commutative. So in the end, we will obtain exactly the same result. Observe as well that as the iterations make progress, half of the threads retire, but the threads that remain active are all neighboring threads. So they belong to the same warp or to the same warps. And this is the third iteration. And finally, we obtain the reduction result. So now we have a program with higher SIMD utilization. How do we do that? By changing this for loop, by changing the value that we assign to this stride, and also in each iteration by checking what are the threads that need to be active, but making sure that these threads with ID T in this particular code, this T is lower than a stride. What means that all those elements with an ID lower than this stride will be active. And all these threads with consecutive IDs are in the end belonging to the same warp. So if we go to this representation, what we would do after, so in the first iteration, observe that all threads are active, in this case with the stride 16. In the next iteration with the stride 8, half of the threads retire, but the threads that retire belong all of them to the same warp, to the same warps, while the threads that continue active also belong to the same warps. After one more iteration, all threads from all these three warps have retired, but all threads from this warp 0 remain active. So in this case, we are maximizing the warp utilization because those warps that are active have many or all their threads active. But there is something more to take into account here, is that after a few iterations, observe that in the last few iterations, the only threads that remain active here belong to the same warp all the time. And this essentially means that we don't really need to store the partial results anymore in the shared memory and then use this intra-block synchronization, this sync thread, to synchronize all the warps and all the threads of the same thread block. Why is that? Because in this case, we are only using threads that all belong to the same warp. So these have the ability or can have the ability to share data without having to go to the shared memory and using sync thread. We can do it in a more efficient way by using the warp shuffle instructions or warp shuffle functions. Let me introduce these warp shuffle functions, and then we will see how to use them in our code. Warp shuffle functions are built-in functions that enable threads to share data with other threads in the same warp. This is faster than using shared memory and sync threads to share threads, to share data across threads that belong to the same warp. There are different variants of these warp shuffle instructions. This shuffle sync is a direct copy from an index lane. Here, if one thread executes this shuffle sync, this thread will read this var variable from another thread that is given by this source lane, or this shuffle up sync, where we copy from a lane with a lower ID relative to the color. So again, we are reading a certain value that is stored in one variable, but we are reading it from a thread with a lower ID at a distance delta. For example, if this delta is 4, thread 3 would be reading the element from thread 4 would be reading the value in bar from thread 0. Or we have this shuffle down sync where we copy from a lane with higher ID relative to the color. So if this delta is 4 for thread 0, we could be reading the var variable of thread 4 if this delta is 4. Or this shuffle XOR sync where we copy from a lane based on a bitwise XOR of the own lane ID. And how do these warp shuffle operations or warp shuffle functions are really implemented in the hardware? This is something we don't really know because the details are not disclosed, but we can try to guess how this is implemented internally in the GPU cores. Observe that, well, this figure here comes from one patent, from NVIDIA that explains how to access a shared memory by concurrent threads. And here in the figure, we can identify the processing engines that are essentially the single lanes where we run the GPU threads. We can identify as well several banks of shared register file that are the shared memory banks. And we also see some local register file lanes. So we see that this is essentially the partition register file that is assigned to the different processing engines and the different threads that will run in them. So if we want to perform a read operation from shared memory, and for now we only focus on how to access shared memory, the shared memory part. Imagine that this processing engine 0 wants to read one element that is in this shared memory bank 2 and wants to move the value to one own register that is in this LRF lane. So what would happen is that the processing engine surrogates the access to this other processing engine because this is the one that is directly connected to the shared memory bank. And by using this crossbar, this interconnect that we have here, we can move the value from the shared memory bank to the register file. And there we get the value from the shared memory. Or we can perform the operation in the other direction, right? We may want to write something to a shared memory bank. So we have one value in one register in this register file lane here, and by using the interconnect, we can write into the corresponding shared memory bank. So by using a very similar interconnect, it would be possible as well to perform shuffle operations within a warp. As I said, this is not something that is explained in this patent. It's only that we are using this figure of the patent to give more or less an idea or a guess of how the shuffle operations are implemented, are executed within a warp on the hardware. So imagine that we want to move some value between different register lanes, between different threads. What we can do, if this is our source value, we can use the same interconnect or a similar one to move the value from this lane 0 of the register file all the way to this lane 1 of the register file. And this is how shuffle operations could be executed within a warp. So by using shuffle instructions or shuffle functions, we can have a more efficient execution of these final iterations where different threads are active, but these threads all belong to the same warp. So what we essentially do in this simplified representation of the tree-based reduction is that whenever we only need to communicate partial results among the threads of the same warp, like these partial results from warp 0 or these partial results from warp 1, we don't need to use interblock synchronizations or intra-block synchronizations. We can use warp shuffle instructions to exchange values across different threads belonging to the same warp. And whenever we need to communicate partial values or partial results across threads of different warps in the same thread block, we have to use the intra-block synchronization or sync threads. And again, if we have to communicate across different thread blocks, we will need some sort of interblock synchronization that can be implemented with a kernel termination or with atomic operations. But this is like, let's say, like a rule of thumb for any implementation that entails sharing data across different threads running together. If these threads are running in the same warp, then they can share data by using warp shuffle instructions. They don't have to use shared memory for that. If we want to exchange data across threads belonging to the same thread block, but in different warps, in that case, we need to use the intra-block synchronization and we need to use the shared memory. So now let's take a look at how to implement this reduction. Let's take a look at our code using the warp shuffle instructions. This is the reduction kernel. Remember that kernels are declared with this global qualifier. And here we have an input array. It's an array of floats. In this case, we have an array of partial sums that is going to be the output of this kernel. And this is the size of the input arrays. So here we define some indices for the threads to know what are the parts of the input array that they have to access with this segment here. And now we have to declare some shared memory array, this input S, where we are going to store the partial sums. And the very first thing that we do for every single thread, we are already reading here two elements, input I and input I plus block dim. This block dim is the size of the thread block. And what each thread is doing here is adding its own element with one element that is at a distance, block dim, two memory accesses here, one addition, and now we have the first addition of this reduction operation being performed and stored, accumulated in this location in shared memory. So after that, we have to synchronize. Remember that half of the threads retire, and the threads that remain will have to use partial results that have been calculated by other threads in the same thread block. So that's why we need to make sure that all these partial results are stable in the shared memory, and to make sure that this is the case, we have to do an intra-block synchronization with these sync threads here. After that, we perform the reduction tree in shared memory. Observe that you can compare this code to the code that we had, shorter code that we had a few slides ago, where we saw how threads started to retire in every single iteration, but the threads that remain are those with the lower ID, so they likely belong into the same warp or the same few warps, and performing this each iteration of this tree-based reduction, accumulating results in shared memory and synchronizing after each iteration. But at some point, we will only have 32 more elements to add, so we only need to use the threads belonging to the same warp, and when that happens, when the active threads are those that belong to the last warp or to warp 0, we don't have to continue using shared memory only for one more addition here. But after that, we can execute this inner loop where the active threads exchange data by using the shuffle instruction. In this case, the shuffle down sync. And observe how every active thread is reading the sum variable from the other thread that is at a distance S tri. And at the very end of the kernel, we have a single partial value, partial result per thread block. So one single thread block of the, one single thread of each thread block, in this case, the leading thread, thread 0, is storing the partial result in the output array of partial sums. In recent architecture, since the Ampere architecture that started in 2020 with compute capability 8.0 and above, there is native support for warp-wide reduction operations. And they can be pretty useful to further optimize the performance of our reduction code. Here you can see the warp reduce functions section from the CUDA programming guide. At the moment, there are warp reduce functions for addition, minimum, maximum, and also for bitwise operations. You have to observe here that these reduction functions only work for integer values as of today, unsigned int and int. But let's take a look at how we could use the in the warp reduce functions in the tree-based reduction. So what we do, we divide the computation in the same way, but now instead of using warp shuffle instructions when we have to communicate partial results among the threads of the same warp, what we could do directly is to use the warp reduce function that is going to use a specialized hardware to perform this reduction operation and probably being much faster. So we can replace this final inner loop that we saw in a previous slide where we use the warp shuffle instructions. We can replace this whole inner loop with a warp reduce function, as we are going to see in the next slide. If we are out of the warp, if we have to communicate data across different warps in the same thread block, we'll have to use intra-block synchronization after finishing the kernel and obtaining one partial result per thread block. We'll have to do again the inter-block synchronization in order to obtain the final result. So in the end, if we want to use warp reduce instructions, what we are doing is replacing this for loop where we use the shuffle instructions, replace it by a single instruction that is, in this case, the reduce at sync. And that's like using the specialized hardware to perform the final reduction of the final 32 elements and obtain a partial result, in this case, per thread block that can be stored in an array of partial sums in global memory. So that's, let's say, the even more optimized reduction code that we could write, that we can write for devices of compute capability 8.0 or higher. As I said before, after terminating this kernel, what we have is an array of partial sums, and now we have to continue performing the reduction of these partial sums. There are different ways of doing it. One of the first one I mentioned is terminating the kernel, moving this array of partial sums to the CPU memory, and then performing the final reduction in the CPU memory, in the CPU. We could, if this array of partial sums is still very large, and we have, let's say, thousands or maybe millions of elements in this partial sums array, we could recursively launch a new reduced kernel and continue performing the reduction. Or we could also use atomic operations, because there is a single thread per block that is that has the partial result per thread block. This sum could be directly accumulated into a global memory location, being updated, being accessed by using atomic operations. Remember that we introduced atomic operations in the previous lecture. Atomic operations perform a read, modify, write operation operation atomically. There are different flavors of atomic operations for arithmetic functions and also for bitwise functions and different data types as well. Atomic operations have the drawback that they serialize the execution, because if we want to have atomic updates, we need to make sure that only one single thread can access a shared memory location that is shared and is going to be updated by multiple threads. So we have to make sure that the updates are atomically. And the problem that we may have here is that if two threads that are running together want to update the same memory location, there will be an atomic conflict and the accesses will be serialized. This serialization is, I mean, it can be it can entail a significant overhead, but that also depends on how the atomic operations are implemented. In older GPU generations, atomic conflicts were much more costly than in today's architectures, because these new architectures have more specialized hardware to handle the atomic operations more efficiently. In the next lecture, we will talk more in detail about atomic operations and how they are implemented in the hardware. For now, we are going to only talk about their uses and how we can use them for the parallel reduction. Remember from our previous lecture as well that there are different uses of atomic operations. We can use them for computation, we can use them for synchronization, and as examples of computation, of uses of atomic operations for computation, we mentioned in our previous lecture histogram and reduction. Histogram is something that we will explain in the next lecture, but let me very briefly introduce you to what histograms are. Histograms are widely used primitives in image processing that what they are essentially doing is counting the number of occurrences of each value in the input image or in the input array, and accumulating these numbers of occurrences. This counts into some bins that belong to a histogram. If we want to perform a parallel histogram, we want to execute a histogram, calculate a histogram in parallel, we will need to use atomic operations, because we may have neighboring threads belonging to the same warp, accessing data from the input image and updating the same memory locations where the histogram resides, and that causes atomic conflicts and in the end serialization, as you'll see. In the next lecture, we will talk more about how to calculate histograms and how to optimize the execution of a histogram. But for now, let's focus on how we use atomic operations for parallel reduction. And before we explain how to use them, let me very briefly introduce you to different versions that you can find among the CUDA samples, different versions of the parallel reduction. I think that it's really worth taking a look at the presentation that is linked at the bottom of the slide, and also take a look, if you are learning parallel programming with CUDA, at the reduction CUDA sample, because it contains different versions with different levels of optimization that are really good when you are starting to program and optimize code for GPUs. There are, as I said, 7 different versions, all with different levels of optimizations, and where you see how first of all, we have SIMD, intra-warp divergence in the most basic version. In the next version, we eliminate, or this version one of the CUDA sample eliminates the SIMD divergence, the intra-warp divergence, by making sure that the active threads are contiguous. After that, it changes the way to access global memory to avoid bind conflicts. then perform the first level of reduction when reading from global memory. Remember from our previous code where in the very beginning of the kernel, we had one thread accessing two locations in global memory, reducing them and then storing the partial result into the shared memory. Then warp instructions, versions 4 and 5 use warp shuffle and also unroll the final warp in order, the final for loop in order to perform more efficient execution. And finally, this version 6 assigns multiple elements to a single thread, and each thread adds these elements sequentially. That's what we call thread coarsening. Is a pretty useful technique, not only for parallel reduction, but also for implementation of many other algorithms on GPU. What we would be doing here, what we essentially do here, if we have a huge array, we are dividing the array into relatively large chunks. Each of these chunks is assigned to a single thread, and the thread is performing a sequential reduction of this chunk. Actually, they don't need to be, let's say, consecutive chunks. These elements might be scattered over the whole input array, and because this way we will make sure that in every single access, all threads of the warp access nearby memory locations. But in the end, because we are doing the reduction, which is associative and commutative, it doesn't really care if the elements being reduced by a single thread are consecutive in memory or are at a certain distance. As I said, this is a technique that we call thread coarsening, and is pretty useful for parallel reduction and other algorithms as well. So these are the 7 versions that are in the CUDA samples. And if you compare the performance of these versions, you'll see how the performance of these versions increases from version 0 to version 6. And actually, you can see here results for 3 different GPUs. These are indeed all GPUs. Is a Fermi architecture from 2010. This is Kepler from 2012 and Maxwell from 2013. But you see that still the optimizations are useful and applicable to the 3 generations, and they continue being applicable for the later generations as Volta, Ampere, or even Hopper. But the reason why I'm explaining these 7 versions of reduction is because we could modify some of these versions to use atomic operations in shared memory and in global memory, and still have let's say efficient executions on depending on the version and depending on the architecture, as we will see. But in particular, in one experiment, let's say just for fun, one thing we did was replacing the final for loop where we performed the tree-based reduction with one shared memory atomic operation per thread. So observe that we are suddenly replacing the tree-based execution that is supposedly, and if it's well optimized, the most efficient way of performing the parallel reduction in a GPU. We are replacing that with an atomic operation to shared memory. And we are doing this for 3 of the versions, version 0, 3, and 7. And this way we generate 3 new versions that are 7, 8, and 9. And if we observe the performance of the new versions that are the red bars, you can see that for Fermi or Kepler, the new versions are not really very efficient, and that makes sense because we are replacing something that is relatively efficient, like the tree-based approach, replacing it with a single atomic operation per thread, and we cannot expect very good performance of these atomic operations, especially in Fermi and Kepler architecture. However, in Maxwell, we see that the performance coming from using atomic operations is even outperforming the corresponding version without atomic operations. So version 7 is way higher, way faster than version 0. Version 8 is faster than version 3, and version 9 is essentially the same performance as version 6. And the reason why this happened is because in the Maxwell architecture, the atomic operations in shared memory were greatly improved by including new hardware for these atomic operations that allowed the architecture to execute atomic operations to share memory in a native manner. So observe how optimizing software is useful and is important for the performance of our system. But if this hardware is improved by adding extra hardware with new functionality, especially if this functionality is important as useful as the reduction operations and the atomic operations, we can see very nice performance improvement. And also with one additional advantage is that we are saving many or some lines of code. Observe how version 7 uses less lines of codes than version 0. Version 8 uses less code than version 3 or 9 compared to version 6, regardless of whether this version 6 uses shuffle instructions or not. So atomic operations, if the hardware is well optimized, can be very useful for performance and also for programmability because we can save lines of code. So we have explored even more the search space of parallel reduction, trying many different combinations of atomic operations to share memory, atomic operations to global memory, the shuffle instructions to exchange data across the threads belonging to the same warp, and different combinations of all of them. We evaluated up to 85 different versions, and for different architectures, we found what were the most efficient implementations with different ways of performing the reduction at different levels of the software hierarchy, the grid, the block, the thread, and so on. And if you want to learn more about the parallel reduction and all these different combinations, I would recommend you this paper that we published in CGO 2019, where we generate code for parallel reduction, efficient parallel reduction using shuffle instructions and atomic operations. And we can go even one step further and use even newer hardware existing in GPUs, the Tensor cores that we have introduced in a previous lecture, and we will talk again about them in a later lecture. These Tensor cores have been proven to also be useful to perform not only matrix multiplications or matrix vector multiplications as they were designed for, but also use them to accelerate operations like reduction and scan. Because in the case of reduction, a reduction can be expressed as a dot product operation and we can get the accelerated reduction using the GPU Tensor cores unit. So if you see what's reduction is, it's essentially the same as a dot product operation, as you see here in this line, where one of the vectors has all the coefficients, all the values equal to 1. So the result will be the sum of the other array, of array A. Also very recommended reading. And if you want to reinforce the ideas that we have covered today, and you want to learn more about performance considerations and about parallel patterns such as the reduction or the histogram, please take a look at these chapters in the book Programming Massively Parallel Processors. This is all for today. We will cover a new parallel pattern in our next lecture. Feel free to contact me if you want to discuss anything about this lecture, or you want to clarify anything, any questions related to the lecture or the course. Thank you very much for your attention. I hope to see you in a next lecture, in the next lecture of our course on heterogeneous systems.